Hello and welcome to our section on describing motion. Probably the first thing that would be important to do in this section would be to ask the question, what is motion after all? So that's one thing we're going to look at. We're going to look at distance versus displacement. What do those terms mean and how are they different? We're going to look at speed. We're going to look at different kinds of speed: constant speed, changing speed, average speed, instantaneous speed. We'll look at all those different things. We're also going to look at graphing, and we're going to look at a distance time graph and what the slope of that line on that graph determines. So let's start with motion. What is motion? Motion is just a change in an object's position relative to a reference point. If you think about that, there is a lot of motion going on in this picture. We have the motion of the airplane. We have the motion of these individuals as they are jumping out of the airplane. We even have the motion of the air moving the molecules through the sky. And it's important to remember that when we talk about motion, we're going to need a reference point in order to talk about that. We'll talk about that more later on, but the reference point, if we use the airplane as a reference point for these skydivers, their motion will be described very differently than if we use, say, the ground as a reference point. And one thing to keep in mind is that in physics, we like to use the x, y coordinates to help us describe motion, and that is something we're definitely going to be using a lot of. We're going to graph things on XY planes. This graph would actually be more appropriately represented on an XYZ three-dimensional graph. There's a lot of motion going on in that picture. So let's look at position. If motion is a change in position relative to a reference point, let's look at two ways that we can describe position. We have distance and we have displacement, and those are really different. You all know about distance. Distance would just be the length that is traveled by an object. It's distance. Displacement, however, is not the same as distance. Part of it is distance. It is the change in position, the distance for the change in position, but it also includes the direction. So it needs both components to be displacement. Here is just an example to give you an idea. Let's say we have a butterfly traveling this little path. You can measure the distance, the total distance that it travels, or you can measure its displacement. Its displacement would be its change in position from A to B, right here, and it would be that direction, maybe 40 degrees. North of east, if you were using a directional frame of reference. You could talk about it that way, but it would need to include both the distance here from point A to point B and the direction that it's traveling, and that would be the displacement. Displacements in the same direction can be added. Let's say we have Joe here. Joe is walking east, and he's walking 5 meters east. That is represented by this line right here. Then he stops, and then he walks 5 meters east again. What is his total displacement? Well, these are in the same direction, east and east. We can just add them since they are in the identical same direction. We can say 5 plus 5, and we can say his total displacement is then 10 meters east. What if our little friend is walking in the opposite direction? Let's say he walks 10 meters east. That's his first displacement. Then he turns around. He walks 5 meters west. What do we do with those? Well, if displacements are in exactly opposite directions, they can be subtracted. So we have 10 meters east minus 5 meters west because it's in the opposite direction. Therefore, his total displacement would be the difference between them, 5 meters east. Displacements that are not in the same direction and they're also not in exactly opposite directions cannot be directly added or subtracted. I'm not requiring that you know how to do these kinds of functions, but for advanced proficiency, look into some of the math that you could use to solve problems where the displacements are not in the same direction or in exactly opposite directions. So now that we know a little bit about motion being a change in position, we talked about that change in position, we talked about distance and displacement. Let's look at how fast we're going, because isn't that a little bit more exciting? How fast are we going from one place to the next? Let's talk about speed. What is speed? Speed is just the distance that the object travels per unit of time. It's how fast it goes. It's the rate of change of its position. So when we talk about speed, speed is equal to the distance per time. Distance divided by time. Here's a nice way we can abbreviate that. If S stands for speed, it's equal to distance, represented by a D, divided by time, represented by T. Distance is measured when we're using SI units. We measure distance in meters. We measure time in seconds. Therefore, speed is always going to be in meters per second in our SI units. Let's do a little bit of practice calculating with speed. Let's say that your speedometer in your car is broken and you would like to know how fast you're going. So to find your speed, you measure out 750 meters and you drive exactly 750 meters. And when you drive 750 meters, it takes you exactly 25 seconds. What is your average speed over this time? First, I'm going to write my equation because it helps to write down things that I do know. I know speed equals distance divided by time. I know that. I am also told in my problem some things I know. I know that I'm traveling a distance of 750 meters. So 750 meters is my distance. I also know that it takes me 25 seconds to travel that distance, so 25 seconds is my time. I can simply plug these numbers in. It's a plug and chug problem. Really easy. I plug values in and I chug away and do the addition, subtraction, multiplication, division. So right here, I'm going to put my time in here. I'm going to put my distance in there. So now when I plug those values in, I can have my formula looking like this. My speed equals 750 meters for the distance divided by 25 seconds for the time. And that ends up giving me 30 meters per second. And I do not want to forget my units. Sometimes you'll see people writing units like this with a little dash. It means the same thing. Meters per second written like this, or meters per second, but units are just every bit as important as that number, 30 meters per second. About what is that speed? Here's some common speeds I just wrote down because we're not used to talking about speeds in meters per second. We usually talk about miles per hour. So here are some correlations. An Olympic 100-meter dash, someone that's really fast might be able to go 10 meters per second. A car that's traveling about 35 miles per hour, that's roughly equivalent to about 16 meters per second. And if you found that your broken speedometer car was registering 30 meters per second, you're going about 65 miles per hour. A commercial airplane would be going about 250 meters per second. So now you try. Pause the video, try this problem on your own, and then when you play the video again, we'll see if you're right. Okay, let's do this problem together. First of all, let's read it. During a lightning storm, you see a bolt of lightning strike 5 seconds before you hear the thunder. How far away was the strike? The speed of sound is 330 meters per second. So here's some things you know. You know that there was 5 seconds. It took 5 seconds for that sound to travel the distance that it traveled. The speed, and you know the speed of sound is this fast, right? So you know the time and you know the speed. And what are you being asked to find? How far away? You're being asked to find the distance. So let's write down our equation. Speed equals distance per time. You know 5 seconds is the time. You know the speed of sound for S. You do not know D. So how are you going to work this problem out? Let's go ahead and fill in plug in the values that we know. So when I do that, I get an equation that looks like this. 330 meters per second equals my distance over 5 seconds. I would like to isolate that D on one side. It's my variable. So in order to isolate that, I'm going to multiply both sides by 5 seconds. Remember, what I do to one side, I can do to the other. So let's do that. So now, 5 times 330 is 1,650. And you can see here that seconds are going to cancel out. So I'm left with meters only. 650 meters on the left side equals, look at my right side of my equation. 5 seconds cancels out with 5 seconds. So I get rid of those. I'm left with simply a distance of 1,650 meters. That's how far away the lightning was. Now let's talk about a few different ideas here. We can obviously have very constant speed. Let's say you set your cruise control to 55 miles per hour and you are going a very constant speed the entire time. It's going to be a lot different than a changing speed, isn't it? If you go a very constant speed, then you can calculate your speed at any time by simply dividing the distance interval over the time interval it took you to travel that distance. Usually you don't, so if you're driving a car, you're not usually going a very constant speed the entire time, unless you're on the highway with your cruise control on. Usually your speed tends to change somewhat. And as your speed changes, we can look at that in different ways. You can look at your average speed maybe over a period of time. Let's say you do you're passing somebody, so you speed up for a little bit and you pass them. Your speed was obviously changing over whatever time interval you're looking at. Let's say you're looking over a 30-minute time interval. You can calculate your average speed over that time interval. It won't be constant, but you could look at the average speed. You can look at how much distance you traveled divided by the time and get your average speed. One way to look at your instantaneous speed is your handy-dandy speedometer. That's a really useful tool, right? Because it tells you your instantaneous speed, whatever speed it is you are going at that particular instant in time. So now let's take a look at graphing motion. We are going to look at a distance versus time graph. This axis will be the distance. We put our time on the x-axis, and remember that distance divided by time is equal to speed. So we can use a graph to actually calculate our speed, our average speed over, if we have constant motion, if we have a constant speed, we can easily look at the slope. Remember, slope is rise over run. And if we know that the rise is the distance, rise on the graph is the distance, the run on the graph is the time, we know that the slope equals the speed. So what is the speed for each of these objects? Let's look at the first one, A. Let's pick some convenient points. Since the speed is constant, we can pick any 2 points and determine the speed for that. Let's pick this point and this point because they intersect our graph nicely. We know that the rise is, if we look over here, it is 2 meters. So for A, we know that the slope is going to be 2 meters for the rise. And what's the run? Right here. How far is that? That is 1, 2, 3, 4 seconds. 2 meters over 4 seconds. Well, that is just 0.5 meters per second for A. Now you pause the video, you calculate the other 3 speeds, and we'll take a look at those in just a minute. Before you see your answers, do a quick check and make sure that your answers are making sense. When you look at this graph, which of these objects do you think is traveling the fastest? Well, you know that this one is traveling more distance per a short amount of time than this one. So as the slope rises up this way, these should be getting faster. Object A should be the slowest, and they should be increasing in speed. Another way to look at that is at 3 seconds, which object has traveled the farthest? Well, D. It's obviously going faster. It has traveled 6 meters as opposed to A has only traveled 1.5. So now let's go to the next frame and you can check your answers. Here are your answers. The speed for object A, right here, speed for object B, C, and D. And that does make sense according to the graph. Here's a little exercise. How would you describe this object's motion? Let's say some object at time 0 has gone nowhere. Here's our distance in kilometers this time. This is time in hours. After 2 hours, the object has traveled 2 kilometers. And it continues to travel, looks like at a constant speed. We have a very straight line and a constant speed that it is traveling. You could take the slope and determine just what that speed is. But at this point here, at 10 hours, it looks like this object got tired. Maybe this person is running or walking along here. This object now is not traveling at all. It is at rest right here. Between 10 hours and 12 hours, this object is taking a rest. Then it continues on with that same constant speed. Here's some advanced ideas. Read these through on your own. How can you add up displacements that are not in the same or opposite direction? Give us some examples. Look back at your math. What are vector and scalar quantities? I'm not requiring that you understand these, but what are they? What are some examples of each of those? Create a speed versus time graph. Represent periods of constant speed, increasing speed, and decreasing speed. And show me what those look like. And I look forward to seeing you in class.